Welcome to the 9th video in the Beginning Artificial Intelligence series. This video is going to cover evolution algorithms, also known as genetic algorithms. These algorithms simulate natural selection in order to achieve a desired result, and are much more easier to understand than neural networks. Basically, you start off with genes, and you make offspring with slightly mutated versions of those genes, and once mutated, their fitness is tested, and those with the best fitness are selected to start the process again. So the first step in this shown through the simulation right here is crossover. So we're going to go look at the crossover. So these are the crossover functions right here. And you can see we have dual, which will take one parent and another parent, and they'll make children with that. We have triple, that will take 3 parents to make 1 child. It pretty much just takes the average. You can change these formulas to make them weighted towards 1 parent or so. And then we have population average, which will take the average of all the parents, and then it will just repeat them and make a bunch of children from that. Population shuffle will shuffle individual genes between parents. Single will pretty much not perform crossover. It will just use out of all the parents, it will just copy those parents to make children. It won't have no parents interact with another parent when you use single. Alright, so the next one's mutation. Mutations, there's 2 types of mutations. We have additive and we have variable. What that pretty much means is additive will actually add to the current value and variable will not. So if we have a we have a range of like 0 to 10 and we're at 5, additive could add to 5. Variable won't. So it would just like say 7. It wouldn't add 2 to 5 like additive would. And then we have our mutation rates, which if we're not using variable size, which pretty much means the genes can get longer or shorter. If we're not using that, mutation rates is a list of floats, which is the rate of the mutations. Then we have distributions, which if we're using a normal distribution, the first value would be, it's a list of tuples or just another list with the means and standard deviations. If this is false, it's going to be the lower bounds and upper bounds instead. And then we have, if you want to round the values, you can. It pretty much will treat it like an integer, the mutations. And then again, the variable size. And then for variable right here, it's same things, and that's pretty much all for that. Then we have size mutations. Size mutations can double the genome, half the genome, and randomly insert somewhere into the genome, and randomly delete from the genome, and first add a gene to the beginning of the genome, and delete from the first, and add from the last, and delete from the last. These are all incomplete functions that will be returned. So when you do these, which I'll explain more in a second, but when you do these, you have to call this function with them. You pass them in a list with here, because if you just double the genes, you'll never get them half, so you'll end up with like really long genomes. Alright, so when you double, that's pretty much just doubles this whole genome. You can, if you give it a value, it will set the double, what you doubled to that value. If you don't, it will just literally copy the entire genome and put it right next to itself. And the genome has to be one-dimensional. If it's multiple dimensions, it will assert this right here. And that's pretty much for all the size mutations. And this one will just cut in half. You can choose if you want to do the left you want to keep, or if you want to keep the right. Random gene addition, same thing with the value again. If you don't give it a value, it's going to just give it a value that was already there. And deletion, this one, same thing again with the value. If you don't give it a value, it's just going to keep the same thing. And that's for all of these pretty much. And then again, for the combined mutations, when we combine the mutations, you give it a size mutation rate. So this is just one float, and it's will it mutate the size. And then the probabilities are the probabilities of which function will be called. So if you have 10 functions and you give it 0.1 for each, then that would be a 10 each one would have a 10% chance of being called when the mutation occurs. So that's pretty much the mutations, size mutations. And then we have fitness, which is up here at the top. Alright, we only have one function here. You can make your own, which is called gene match. Pretty much what this does is it takes the squared mean error of what the genome that it's thinking it is from the offspring, and then what the actual genome you want is. So this is more for test cases. It's not necessarily for actual. It's just to make sure it works is really what this function's here to do. And so you can see if we have variable size, you have to use this function, which has to go to each individual genome. This one, just because it's a NumPy ND array, it will just do it all. So this one's a lot quicker. So when you use variable size, it slows down the algorithm quite a bit. And now we have selection. You have two functions here. You can do select greatest and select lowest. What this will do is whatever fitness value you get, is the best one greater, higher fitness values, or lower? So because this one, like for the gene match, you want lower, that means it's closer, so you would do select the lowest. If you want if you're doing an actual fitness type of thing, like if you have these things, you're going to get a better fitness score, then you would want select greatest. And now we can go look at the actual evolution algorithm right here. Pretty much it will take all those functions that we just went over and saves them, and then you can simulate them. You can simulate them with islands or without islands. When you simulate like this, it's a little simpler, but you can simulate with islands, which will pretty much run kind of parallel simulations, and then depending on your number for migrations, it will migrate those islands every once in a while. This can be threaded if you enable as true. Of course, Python threading is not the best because there's one global interpreter, so it'll actually be slower if you enable this, but it does depend if you're doing computations when you're doing your fitness scores or something. So like if we were training a neural network, or if we were using NumPy, some NumPy functions will actually release the global interpreter. So this being true could be good, but sometimes it's not, especially if we're just doing normal Python code and not using NumPy or stuff like that. And so those are the two functions here, and that's pretty much it for going over the evolution algorithms. But in the next video, we will go over hyperparameter tuner, which I'll just show the code a little bit right here, because in the next video we'll actually be using it. You can see you have your hyperparameter tuner, and these are just initialize some things to keep track of stuff, and this is how you tune. So this is pretty similar to the simulate up here in evolution algorithm. It actually uses it. If we look at the code, you can see down here, yeah, we call simulate. So it doesn't do an island simulate. I was thinking of adding it, but I didn't, because I think a simulation is pretty good, especially it's good enough. And so you just pass the generations you want, the population you want, selection size, and then you make a function which will use hyperparameters. So when you make a hyperparameter, if we go look at, so we have right here we can make a uniform hyperparameter, a list hyperparameter, or a Boolean hyperparameter. And if we go look down here, you can see a uniform one will choose anything from 0 to almost 10, and anything from 0 to almost 5, and then a true or false for this. And you can see how this function looks. We pass it into the tune, and it will actually find the values that get the lowest error, because if we look at the tune up here, we have lowest best true. So if you wanted higher fitness values to be good, you would disable this. And I didn't give it a crossover function. That means it will just be default to single, which means they are not actually crossovering. And if you enable this to true, it will just be verbose, which when you look at the verbose for simulations, it will just print out the generation, the highest fitness value in that current generation, and the lowest in that current generation, and the mean of that current generation. And so yeah, that's pretty much all that. And if you have any questions, ask in the comments section below. Goodbye.